Okay, so I'm recording now, and the idea here is we are going to take some raw 3D output from Rayleigh and go through the steps both at the command line and in a Jupyter notebook to get that into Vapor format. And then I'm going to illustrate how to visualize the 3D data in Vapor and also how to plot flow lines or magnetic field lines, okay? All right, so I've actually already got this tar ball. So I'm going to, first, I'm going to build the interpolator. Okay, so I'll go to my forks directory to the Rayleigh master branch, and I'm going to pull the latest version. Okay, there we go. We've got a Vapor visualization notebook. And I've activated my conda environment, so that's this little RA dev. So the compiler I have access to here is a GNU compiler. And so to build the interpolator, I'm going to say make interp3d.gnu, okay? And you should see something like this on your screen. And then if you look in the bin directory, in this case I had a debugged version of Rayleigh there also, but I have interp3d, okay? So the idea here is that we need this helper program. And what this is a interpolation routine written by Kyle Augustin, does a tricubic convolution interpolation. I think Kyle could comment more on that than me. What I basically did is I put a command line interface around it so that we don't have to modify an input file anymore. And instead we can just drive it from the command line. So this lets us script this little routine. And what this does is this takes Rayleigh's 3D output, which is on a spherical grid, which is non-uniform in radius and non-uniform in latitude, and it interpolates it onto a Cartesian grid, which is uniform in all directions. Okay, so you can try this little program out. If you just type /interp3d, you'll get an error message telling you haven't specified the proper input flags. If you run interp3d-h or --help, you'll see a little description here of the different flags that you can pass to it and two examples of how to call it, okay? And so there's two ways to run this program. One is that you take one scalar data file, like a 3D output of temperature, say, and you output one Cartesian gridded version of that variable. Okay, so that's where we have here, we see that the little help menu says scalar mode, okay? And the syntax is pretty simple. You just say -i, give it an input file name, -o, give it an output file name, and then -n, and you give it a number, and the number tells you how many points there are along each direction of the cube, this output, okay? The other way you can run this is in vector mode, and this is really useful for Vapor. You can take files that correspond to the r, theta, and phi components of a given vector field, and you can output those on a Cartesian grid, but you output the Cartesian vector, okay? So you take a spherical vector on a spherical grid, 3 files in, and then you output 3 files which are the Cartesian components of that vector, and they're on a Cartesian grid, okay? And so we're gonna go through both of these momentarily. And then if you scroll down, there's some other flags. The big one right now that you also have to do is you have to specify one grid file, okay? So we'll see in a minute when we output 3D data in Rayleigh, right now there is a data file and there is a grid file. Soon, I'm going to stop doing that and put the grid information in the header of the 3D output file, or possibly in a footer. It looks like that's easy enough to just read from the end of the file. That way it doesn't mess with any other routines somebody has already working for this. That way, though, we won't have a grid file for every time step. But in any event, we also need to tell it the grid for right now. The program is already set up to work with data where the grid is wrapped into it, but Rayleigh doesn't actually output that yet. Okay. A couple of other things that are possibly interesting here. If you want to output the magnitude of the vector as well, so you want to have 4 outputs, you can specify an additional file here. You can output in double precision if you want to, if you're trying to do some kind of actual math on the 3D grid instead of just visualization. But in general, single precision output is just fine for visualization purposes. You can zero out data below or above some value in radius. Okay, so that's the Rmin and Rmax flags. So if you've got something you're trying to look at in the interior of your domain and the boundaries are kind of getting in the way when you try to visualize it, you can use these flags to try to zero out whatever's going on there. Okay. There are these 2 flags, RPM and RSM, so you can remove the phi mean from the data. So if you want to remove the differential rotation from V phi, for instance, you can pass it the RPM flag. Or you can remove the full spherical mean at each radius with this RSM flag. Okay, this is really useful for things like temperature, which have a significant L = 0 component. Sometimes that makes it difficult to visualize the temperature unless you subtract out the spherical mean, and we'll look at this in just a minute. Okay. Okay, so any questions on any of that before I move on? I should get my
Nick?
Yes.
So in a vector field, so can we generate such as a spherical components of vector on a Cartesian grid, such as, for example, so sometimes we want to display we want to render a radial velocity or some of the phi component of the magnetic field.
Yeah, you can absolutely do that. No, this is just for vapor in particular. This is just some helper functionality. So what you would do, and what you're saying is, can we still have the spherical components of the vector on a Cartesian grid? Yeah.
Yes.
Yeah, absolutely. You just run each of those as though you're in scalar mode. Okay. The point of the vector mode is that for vapor in particular, at least you used to, I think you may still need to have the Cartesian vector in order to plot the flow lines or the field lines. Okay. And so this is additional functionality. You can take anything that Rayleigh outputs and just input that variable on a Cartesian grid.
I got that. So to get to make such a data,
Yep.
so we need to use a scalar version, eh?
Yeah, exactly. Yeah, okay. You could do that with just the scalar version. The point of scalar mode really just means you're not thinking about a vector per se. You've got an input file and an output file.
Okay.
Okay. Okay. So what I'm going to do now is I'm going to change to I'm going to create a fresh directory. So I'm going to make one called telecon. Okay. And then I know that back in my viz demo directory, I have a copy of this tarball. Okay, so my full2.tar. So I'll just move that over here. So I've got an empty directory, and I'm going to extract this tarball with tar xvf Rayleigh full.tar. Okay, and that gives me a directory named spherical3D. If I look in there, what I have is I have a bunch of outputs. I have 5 time steps of data, and at each time step I've output 7 quantity codes. I've output 1, 2, 3, which is velocity, r theta phi components. I've outputted 301, 302, and 303, which is vorticity, and then I've output temperature, which is 501. Okay, and then I have a grid file in each of these for each of these time steps. Okay. So the next thing I'm going to do is I'm going to copy that interpolation routine over. So feather, devel, forks, Rayleigh, bin, interp3D. Okay. And what I'm going to do here at the command line, it gets a little tedious if we want to do multiple time steps. So I'm just going to go through one time step. We're going to create data where we have the temperature with the spherical mean removed. And where it's not removed, and then we'll convert the velocity field into its Cartesian vector equivalent. Okay, so I just say dot slash interp3d. So for temperature, we'll say out, I'll call it temp.cube. The input will be spherical 3D, and I'll grab one of my temperature files. Okay, and then I also need a grid file. All right. And I see the terminals a little bit. Okay. And we'll do a cube that is 256 cubed, and I'll do -v for verbose. Okay, so I'll output this to temp.cube. I input one of my temperatures, and I give it a grid file. Okay, and you'll see some output, and it will tell you how long it took. This thing is OpenMP enabled, and so it will, by default, OpenMP, I think, just lets you use all the cores, but if you want to just use 2 cores or something like that, you can set the OMP num threads variable. So if I do this with 2, it'll probably take a bit more than half a second, probably like 1.2. Yeah, okay. In my case, though, I've got 6 cores in this machine, so I'll just keep it at 4. Okay, and then if I look in my directory with ls-l, I see a temp.cube file. Okay. So what I'm going to do now, I'm going to set an environment variable for this grid file. So spherical 3D. Let's give it a grid file name. Then I don't have to keep putting that in. Okay. Now, the next thing I want to do is I want to create cube data for the velocity field. So I'll say interp3d, and then instead of -i, it needs to know that it's doing vector mode, so we give it -ir, which is in the help menu. Okay, then -it for the theta file. And -ip for the phi file. Give it the grid file. And then we need to tell it the cube dimension. And then we say -ox, and we'll say temp.x, -oy, temp.y, -oz, temp.z. Okay, and we'll do verbose as well. All right. So instead of -i and o, I have -ir, -it, and -ip. And then instead of -o, I have -ox, -oy, and -oz. Okay. And I mistyped something. I put an extra slash here on accident. Okay. All right. And now if I look around, I've got temp.cube, which is my temperature. I should have named that something a little better, but then I've got temp.x, y, and z, and so that's my vector field in Cartesian format. Okay. All right. So the next thing I'm going to do is I am going to create, so we're going to take this now, and now we're going to use Vapor's tools to put this into Vapor format. Okay. So the 2 tools we're going to use are, one is called VDC Create, and that's for Vapor 3, and raw to VDC, or for Vapor 2, and I'll do both, we just replace the VDC with the VDF. Okay, I'm not sure what VDC stands for, actually. VDF, I think, was Vapor Data Format. Okay. So the first thing I have to do is I need to put those in my path. So export path equals custom software Vapor 3 Linux bin path. So if you're running on a Mac, I think you can just type these commands. But in Linux, you always have to do a little bit of gymnastics with your path. Okay. All right. And so the idea here is that when we create a Vapor data set, it's pretty simple. I'll start with the VDF create command. So this is for Vapor 2, but the VDC create works the same. You'll see this in a second. So we say VDF create and then dimension, and then we tell it the dimension of our cube that it's going to be reading data from. Okay. We tell it how many time steps are in this data set, and there's just one for right now. And then we give it names for the 3D variables that we want to use. Okay. And so in this case, I have 4. We separate them by colons. So I have temp X, Y, and Z. And we'll call this v2test.vdf. Okay. So I say VDF create, and there's no output, but if I look, I have a little VDF file there. Okay, so basically that's a bunch of metadata that tells the routine we'll use in a minute what to expect. Okay. All right, I'll run the other command. So it's VDC create. And I do advise you to give these 2 different names because they'll both have a directory that if you give them the same name, even though one is VDF and one is VDC, there'll be a directory that has the same name for both of them. Okay, so I'll call that v3test.vdc. Okay, and if I look, I see I've got a VDF file and a VDC file. Okay, so the next thing we need to do is we actually need to load this data into our data set. And 1 second, we pull up the command here. Okay, so we'll start with the Vapor 2. So the command is raw to VDF. We need to give it a flag for the time step. So I'll say time step 0. So there's only one time step in this. The time steps start at 0. We can have multiple time steps. It's probably easier to do that with the Jupyter Notebook, or you want to script this. So we're going to load into the variable X of our v2test.vdf. And then we want to give it the name of the file. So in this case, the cube file that is, so temp.x. Okay, and you'll get some output like that. All right, and I'll do this for my other 3 variables. So y, temp.y, z, temp.z, and then temp. I stored that in temp.cube. Okay, and it gives you a little bit of information. It tells you every 10 slices of the data that it's reading. It tells you how long, but the useful thing is it tells you the min and the max. So that kind of is like a sanity check. So in this case, the variable I'm reading is temperature. And so the boundary conditions are 0 and 1. And don't forget, we did a little interpolation, so it's okay that it's not exactly 1, but we see that the min is 0 and the max is very close to 1. Okay, so I think all that worked. Okay, and now I'm just gonna, oh, thanks. Hero put into the chat for anyone who's trying to do this on a Mac, some information about where these commands are stored. Okay. All right. So the next thing we're gonna do is we're gonna do the Vapor 3. So we'll just change this VDF to VDC, and we'll run through all this again. So that was called v3test.vdc. Okay, and so I'll do the X component of the vector field. This one, by the way, doesn't output. I think you can give it a -v. There's a dash verbose. There. Well, I don't know. I thought it would tell you what it was doing. In any event, there's my X variable, and I'll do the Y. Okay, then I'll do Z. And then I'll do temperature. Okay. Okay, and that is the last of the commands that we'll run at the command line. You can see why you'd want to script this, and this is why I wrote the Jupyter Notebook file. Okay, but notice, by the way, that when I did this, for my VDF file, it's called v2test.vdf. I have a data directory, which is v2test_data. And then for the VDC file, I have a v3 test underscore data. Okay, so the Vapor data set is really the directory and the metadata file. Okay, so if you're ever trying to move things around, you want to move both. Okay. And then I think what we'll do before I get into Vapor, oh, and I forgot to remove the spherical mean on the temperature. So that's interesting. We'll have we'll see what that looks like when we try to render it in a bit. But what I want to do now, before we actually open up Vapor, let's run through this process with the Jupyter Notebook. Okay. So what I'm going to do is from my Rayleigh directory, which is in forks or devel, forks, Rayleigh. In the post-processing directory of Rayleigh, there is a Jupyter Notebook for Vapor. Okay, I'll put a Python script there later. I meant to export this as a Python script as well so that you can run it without the notebook. Oops. So I copied it here, and then I'll open this up. Jupyter Notebook, Vapor Notebook.ipynb. And this notebook is still a little bit of a mess. I moved some things around. I'm going to clean this up and sort of make it like the Rayleigh Diagnostics notebook, where there's some markup in here, and then some kind of description of what's going on, and then you see the cell, and this should load nicely into the documentation that way. But to start with, the main thing you need if you want to create a data set, a Vapor data set with this notebook, is you need from Rayleigh Diagnostics, you need to import Rayleigh Vapor. And this reminds me that I did not put the Rayleigh Diagnostics file in this directory, so I'm going to do that right now too. So that's also in Rayleigh post-processing, Rayleigh Diagnostics.py. Okay. So this class basically handles some data organization and then scripts this stuff we just went through automatically, runs it in the shell for you, and creates a Vapor data set for you. So I'm going to go through this. The other thing that I import, I have this little helper routine gen 3D file list. You don't need to use this if you don't want to, but it's helpful. Okay, and we'll talk about what that's used for in a minute. All right, so the first thing is I want to say, where does the data sit? Okay, and in my case, I am in Home, Feather, and Viz, and Telecon. Okay, so you may want to modify yours appropriately. So that's where the run is. I'll use that to kind of tell it where I want to put my Vapor data sets. Okay, and then we have a, it needs to know where the actual data is, so I give it the spherical 3D. Okay. After that, I specify one grid file. Even though I'm going to use multiple time steps in this example, we just need one grid file. The grids are all the same. Okay. And then I need to tell it a name for my Vapor data set. And since we just made two called V2 test and V3 test, I'm going to use something different. Okay. So I'll call this one RA Viz Demo. Okay. You want to omit the .vdc and the .vdf here. Let the class, this Rayleigh Vapor class, take care of that when it sets everything up. Okay. The next thing I want to do is I want to say where interp 3D is located. So that's the Rayleigh bin directory. In my case, I don't know for sure. I have one sitting in my fork, so I point this to where I stored my master branch of Rayleigh. Okay. And then you can create a little temporary directory somewhere. This thing will by default just write a few temporary files, these cube files, basically to the directory you're working in, and then it will delete them when it's finished. I would suggest create a directory somewhere that you know is empty, and so that when it automatically deletes it, there's not some kind of redundancy between those file names and something you have in your directory. Okay. Okay, the next thing I want to do here is, because I'm working with both versions of Vapor here, I tell it which version I want to use, and I'll run through this with both of these. But basically for Vapor 2, I just append a little V2 onto the end of my file name here. Okay. But what we want to know is we want to know where those programs, raw to VDF and VDF create, and raw to VDC and VDC create are located. And we specify that with this vbin variable. Okay. Then there's just some stuff down here you can ignore. I need to clean this notebook up. Okay, so that's just telling, that's kind of getting all the file handling set up, right? Where are we storing the data? What version of Vapor are we using? Where is Vapor located? Where is interp 3D located? And we have temporary directory. Oh, and I also specified the size of the cubes, okay? So you can change this to whatever you want. This could be 512, it could be 64, it could be 1024. I would suggest leave it at 256 for now, especially if you're processing this full data set, because it gets a little big. Okay, the next thing we need to do is we need to supply some information about the actual files we want to process. We told the class some information about where it is. We haven't actually created the class yet. We'll do that in a minute. Okay, and that's where I use this helper routine. Okay, so what I do is I just specify the first time step and the last time step and how many time steps are in between. Okay, so in my case, I was outputting every 20 time steps. The first data file was 278,020, and the last one was 100 time steps later. Okay. And then what I'm doing here is I'm actually only concerned about the scalar variables right now. Okay, so anything I want to render just as a scalar and not worry about the fact that it may have other vector components or something like that. And so I want to look at temperature. And I'm also going to look at V-phi. So I give it the Rayleigh quantity codes for those two, and that's just a regular list in Python. So brackets, values separated by commas. Okay. And then I give it the names that I want those quantities to have in the Vapor file. Okay, so these could be whatever you want, but 501, which is temperature, will be mapped to a variable named temp in the Vapor file. Okay. And value 3, which is V-phi, will be mapped to a variable which is called V-phi in the Vapor file. All right. And then this little routine generates a list of files for me. And I have some notes here on how this is structured, but basically this is a 2D list. Okay, and so the first element of the list is itself a list, and that gives you the file at time step 0 for each quantity, right? So in this case, we'll look at this. Actually, I need to run this notebook. So let me go back. I'll run the first cell. I'll run the second cell. Okay. And then when I run this, it prints the file list for me. All right. And so if I look, the first element is right here. So I see I've got the first time step for 501, and then the first time step for quantity 3. Okay. So just respect that structure, and you can create your list however you want to. All right. And then the second time step is the second element of this nested list. And then I have that for 501 and for 03 as well. Okay. All right. There's a bunch of notes down here, but the main thing is that if we want to remove the spherical means, we can. So we just create this list and we give it true or false values. You don't have to specify these. You'll see how all of these are passed to the class creation routine a little bit further down. But if you so this is a completely optional keyword. By default, it will not remove the means. But if you do want to do it for one, you have to specify true or false for all of them. Okay, so if it's set to true, it will remove the spherical mean for that corresponding quantity, right? So we're saying here we do want to remove it for temperature, and then the second quantity is V-phi. We don't want to remove it for V-phi. Okay. Similarly, you can pass the Rmaxes and Rmins. These are also optional. So if I wanted to zero things out near the boundaries, for instance, I could give these the actual value. So I have some notes here on that. Okay, in this case I don't, but I actually pass it below so you can experiment with this if you want to. So I'll run that cell. Okay. All right, so in this data set we had velocity and vorticity. So it can be interesting to render vortex lines as well. In fact, I think that's what we'll do when we load this in Vapor. So what I need to do is for each vector, I need to specify the quantity codes that correspond to the R, theta, and phi components, okay? And I have a list for each vector. So for velocity, I have a list with 3 elements, 1, 2, 3, since those are the codes for VR, V theta, V phi. And then for vorticity, I also have a list, which is 301, 302, and 303, because those are the vorticity component codes, okay? Then for each of these, I generate a list of files by calling this 3D file list routine. So each of these gets its own 2D nested list, all right, just like we ran above. Then I also need, for each vector, I need a list that tells Vapor what those variables will be called in its data set. Okay, so when we open the Vapor data set, I'll have Vx, Vy, and Vz. And then for vorticity, I'll have Wx, Wy, and Wz. And then I'm also going to have it output the magnitude of vorticity. So I'll give that a name, so Wmag. The class creation routine expects either a 3D list or, excuse me, a 3-element list or a 4-element list. So if there's a fourth element, that whatever we call this, we could call this, Tom Jones or something. Tom Jones would get the magnitude of this vector, whatever it is. Okay. So in this case, just by passing 4 elements, it will say, all right, we'll compute the magnitude of the vector and we'll map that to this variable name. Okay. Then I take all these things I've set up and I create a nested list of those. Okay. So I have a list here of vector names, and then that's just a comma separated list of these arrays right here. Okay. And then I also group the file lists together. All right. So what was a 2D nested list has now become a 3D nested list. Right. Basically, just stick to this format if you want to do multiple vectors, and it will work. All right. So I'll run that, and it prints the files out for me. Okay. All right, and then what I want to do is I just create an instance of the Rayleigh Vapor class. And here I'm passing all the different optional keywords to it. Once it's created, once that instance is initiated, I can tell it to actually create the data set. Until that time, it doesn't actually create a VDC file or a VDF file or a corresponding directory on your machine. Force equals true means that it will attempt to delete those files before it creates them. Okay. So I'll run this. And this is the part where it works for me, but it probably crashes for everybody else. If something is going wrong, you'll probably see some output over here in your Jupyter Notebook window in the shell where you started that from. Okay, but that ran fine. And then I'm going to run this populate dataset command. So what this is going to do for all of these input files we've given it and all of these different scalar and vector parameters, it's going to go through those file by file, create a data cube on a Cartesian grid, and then load it into the Vapor dataset. Okay. So I'll run this. Oops. And it gives you a little bit of output. It tells you it's converting the data for time step 0 of 4. In a moment, we'll see time step 1 of 4. And it takes a second. It's a pretty big data set. The files themselves aren't that big, but we have a lot of files and we're doing a lot of things with them. Okay. Is this working for people that are trying to follow along? Okay, and then I'm going to run through this again, but change my Vapor version to 3. By the way, for anybody that's getting a little bit of cabin fever, I've discovered that since nobody can play soccer in the parks, there's some great places to launch model rockets now. Just a thought. Though Michael's is closed down now, so you have to order them from Amazon or something. Okay, almost done. So for anybody that's following along, did this work for you? Can you type it into the chat window? I'm just kind of curious. I know Kian tried it out for me. Okay, so this is all done. So now I'm in this directory and I'm just going to do a ls-l. And I see, okay, I've got a VDF file and a VDC file that I just created. Okay. And then I have some corresponding data directories. And if you're doing the full data set, the Vapor 2 data is about 3 gigs, and I think the Vapor 3 data is just a little bigger than that, maybe. Yeah. Okay. All right, so this looked like it worked. Before I go on, so we've taken Rayleigh data, we've put it in a cube, and then we've put that into Vapor. Does anyone have any questions about anything before we actually look at this in Vapor?
Hey, Nick.
Yeah.
Is there like a remove axisymmetric mean option, or?
So I forgot to put it. So I forgot to put it into the into the Python class. I will do that soon, but
Okay.
for the moment there's not. But you can do it manually with interp3d. That's the RPM. Remove the phi mean RPM.
Okay, I see. Thank you.
Mm-hmm. Okay. All right. So with that done, I'm going to just shut down this notebook. Okay. And I'm going to completely clear out my conda environment here. All right. And I'm going to run Vapor. So we'll start with Vapor 3. What I've decided, having been playing with this for the last week or so, is that, in my opinion, the volume renderer in Vapor 3 is probably better than Vapor 2. But the flow lines are not, okay? And so we're gonna go through this with both of them. But we'll start with Vapor 3, all right? So I type in Vapor 3. Let's see, let's just close that. I want to keep that though for when I move into Vapor 2. So I'll just make this big. Okay. Uh-oh, my X is doing something there. We'll see in a minute. I don't know why you're seeing the beach background back there. All right, so what I'll do is I'm going to load a data set into this session. So I'll open a VDC file. I'll navigate to the directory. So I was in viz telecon. And we'll just grab the full one here, ra_viz_demo.vdc. Okay. When I open that up, I see a box here. I can click on it with my mouse, drag it around. If I right click, I can zoom in or zoom out by dragging the mouse around. Okay. But right now, we don't actually have anything visualized here. So what we have to do is we have to decide what kind of visualization we want to do. So I'm going to move over here to this button, New, and a little window like this will pop up. Okay. And then I want to start with a volume rendering. So I'm going to click Volume, and I'll click OK. All right. And now the tricky thing, at least on Linux, there's actually, it took me a little while to understand what was going on. Over here, I don't know how well Zoom shows it, but under Enable, there's a checkbox. And it's very hard, because it's highlighted blue, to see that there's a checkbox. But I have to check this. Okay, and when I do, suddenly some massive junk appears. Okay, and I think the way you're oriented is that you're looking down the rotation axis when this starts out. Okay. All right. What I'll do first then, so I can rotate it around. I can zoom in and out. But the problem here is that we've got a lot of data that has some opacity to it, which is uninteresting. In particular, we see all the zeros in the cube, okay, and we need to get those to go away. So next to variables, there's a tab called appearance. I'll click that. And what we have here is a transfer function, okay? And so there's two pieces to this. But the first thing I'm going to do before I do anything else is what you're seeing here is a histogram of the data, okay? If I right-click this, I can change the histogram scaling to logarithmic, okay? And that makes it a little easier to see where your data sits, all right? And so the x-axis here is the value of your data. And based on the value, it has a color that's being mapped to it. And the default color table they give you is this red to blue. If I right-click, I can add control points to this color table, and we'll see what those do in a minute. So maybe add 2. So I'll right-click kind of down here near the end, both ends. And when I click that point, if I want to, I can change the color here by clicking this box, right? So each of these little points, if I click it, a little black dot appears, okay? And then I can change the color associated with it by going to this, clicking the little color box and choosing something, okay? So you can play with that, all right? The y-axis on this thing is telling you, this is just the histogram of the data, right? So it's telling you how many points there are in some bin on your x-axis. But then the other thing that's useful, or that we're really going to make use of here, is the opacity. So these little buttons up here, you can drag these around, and that controls how transparent or how opaque that particular data value is, okay? So what I'm going to do, I'm going to right-click that line, and I'm going to add one more control point, okay? And what we're going to do is most of the uninteresting stuff sits at a 0 value in this data set. And that's about where this big peak is. So what we're going to do is we're going to make everything around 0 become transparent. Okay, so I'm going to drag this line down. Okay. Then I can move this dot over, and it tells me what data value I'm at. So I can actually type in here if I want to. So for instance, I can make this 0.00025. Just basically where it was, and I can make it kind of symmetric about 0. This could be minus 0.0025. Oops. Well, they're very close, but that's okay. All right. So now if I rotate this, I see my temperature field. I see warm and I see cool, but it looks kind of bad right now. So what I'm going to do is I'm going to go back over to the variables tab, and I'm going to tell it that I want the highest fidelity for this visualization. Okay, so the idea is that Vapor stores your data in different successive levels of refinement, and you can work with the coarsely refined data or the highly refined data. I'm not sure what Vapor 3 does, but Vapor 2 actually does a wavelet transform, and so it basically does 3 levels. Usually, I think you can specify more of a wavelet transformation. Okay. All right. So there's my temperature field. If I look down from the pole, I can see some convective cells, and then there's this big cool region because nothing's going on at the equator. This is actually kind of an interesting simulation. This is something I'm working on with Freddie Ramirez, who's on here. What we've done is we've put a centrifugal term into Rayleigh as well. And so you have regular buoyancy, you have Coriolis force, and then you also have centrifugal buoyancy. And so the Froude number for this case is about a half. So the centrifugal term is about half as strong as the regular gravity term. And so what it's doing is it's tending to kill convection at in the equatorial region. Now, if you look at this, you can see that there's probably some sort of columnar structures in here, and maybe we'd like to look at those. So what I'm going to do is I'm going to go back over to the Appearance tab, okay? And I'm going to play with my transfer function. What I'm going to do is I'm just going to make everything that's cool absolutely invisible. So I'm going to grab this last dot and drag it down. And now we're only seeing temperature perturbations, which are larger than 0. We're not seeing any negative temperature perturbations anymore. And so now we can sort of see the structure in this thing. Okay. And if I want to, this looks a little bit washed out. I can start to drag my color values around. Okay. Maybe I'll add another control point. Sometimes what I like to do is I like to put a really dark shade of red at the end and then sort of drag that down. And sometimes this works really well. It kind of looks like it adds shadow to it. And then maybe down here, I want to add another control point. Actually, that's the one I want to be dark. So I'll make that one dark. And I want this to go, we'll make this sort of yellow. There we go. Okay, so you can play around with this and get sort of the right accent. By the way, can everybody see this? Is this coming through on Zoom? Like the actual visualization?
I can see it.
Okay, cool. Thanks. All right. So anyway, that's sort of how you visualize a scalar variable in Vapor 3. If you scroll down a little bit, you'll notice there's some other things like I don't really know what these do. Do the sampling rate. I played with this. I haven't really seen it change very much that my eye can pick up on. You can play with the lighting, so we can make things shinier. You can play with this anyway. Okay. Oh, there we go. Specular's nice. All right. So that is we've rendered a scalar field. Now let's actually look at a flow field. Okay. So I'm going to come back up here and I'm going to add another visualizer. So I'll leave this one on, but I'm going to make it invisible for right now. So I'm just going to uncheck enabled. I'm going to click new. And we're going to select flow. Okay. And we'll hit OK. And then again, like before, we need to check enabled. Okay. All right. So there is some kind of flow and it looks really weird, but the reason is that there's no variable mapped to X, Y gets V phi, and Z gets the magnitude of the vorticity. Okay, so we need to change this. So let's look at the velocity field. So we want to map X to Vx, Y to Vy, and Z to Vz. Okay, there we go. Now we've got some squiggles. Okay. We'll go ahead and put this on high fidelity so that when it integrates the streamlines, they actually look reasonable. And then I'm going to go over here to seeding. Okay, so the idea is that Vapor randomly seeds the domain with points and then integrates the streamline for some distance. Okay. And what I'm going to do is on each axis, so instead of gridded, we're just going to give it a random distribution, so on seed distribution settings. And then we're going to add some flow lines. So let's do, instead of 50, let's do 200. Don't go crazy, by the way, at first. Get a feel for how much it changes when you add more flow lines. If you add like 3,000, your computer might just freeze. Okay, let's see, let's try 300. Okay, and there, now we're seeing something in there. And I'm trying to remember if we integrate for longer, if I change the integration steps to 200, I think that's just the accuracy. Oh no, it does. It actually traces the flow lines a bit longer. And so you're kind of able to see some structures up here. If we look down from the pole, you can see some vertical looking structures. I'll let you play around with this. I am not really happy with this as a flow renderer right now. And this is why I want to have a look at Vapor 2. Okay. Before I move to Vapor 2, one thing I will mention though, we can reactivate our volume rendering and we can render these together. Okay. So we can turn one on, off, etc. Okay. All right. So before we move over to Vapor 2, does anybody have any questions or thoughts or anything?
I have a question.
Mm-hmm.
Right.
I'm going to have to leave here in a minute, but in your directories that you showed, are there already these data cubes that I can just read right into Vapor, so I can play with Vapor with these already?
Yeah. So on that website I sent, there are some Vapor zip files.
Okay.
And yeah, you should be able to just unzip those. I zipped them in Linux, but I tested unzipping it in Windows and it worked.
Oh, I see. They're the Vapor 2, small, large, Vapor 3. Yeah.
Right. So the smalls have 1 time step and the larges have the 5 time steps like we have here.
Okay, cool. Thank you.
Yep.
Nick?
Mm-hmm.
And so in data on a cubic box, so the value at the outside of the speaker shell is filled by 0.
Yeah. Everything outside the domain is filled by 0. Yeah.
Okay, then so we have to be a little bit be careful to treat to plot a 0 value. Right?
Yeah. I mean, usually when you're doing
You don't do this, but
rendering, the 0 value isn't interesting. I could probably add a flag in there at some point so that it fills it. There may even, Kyle may have already put that in there. I'm not sure.
honestly, I never plotted a 0 value in my results, but that's all. That could be okay, but
the one other thing I thought I should mention before we leave Vapor 3 is that if you want to animate this, so this data set has 5 time steps in it. If we go to capture, no, not, that's where you do the image sequence. I think it's navigation. So up here next to renderers, there's a tab called navigation. And then below that, there's a tab called animation. And if you just hit play, it will start loading in the data from the different time steps. Okay. So once it's loaded in, it's usually faster. So if I run it again, we can start to see it animate. All right. And so it's always slow when you animate it in Vapor, but you can go up here to capture and you can tell it to start capturing an image sequence. And you use this in tandem with the animation feature, and you can generate frame after frame after frame and make a movie. Okay. All right, I'm going to close Vapor 3 now. And I'm going to open up Vapor 2.
Nick,
Yes.
can you script everything you just said into Vapor?
I'm not sure what sort of scripting support Vapor has. I'm really not sure.
Okay.
Yep. Okay, so I'm in Vapor 2 now. And Vapor 2 is a little different. So we want to go to data, and we want to load a data set into the current session. Okay. And so I'm going to grab the 5 time step VDF file we made. Okay. And here I just click, there's a little thing here, I think it actually says instance 1. So I just need to click the checkbox under view. I'll go ahead and put this on high fidelity. And then we can see the different variables here. So I'm looking at temperature again. Maybe I want to look at the magnitude of the vorticity. Okay. And then we can play games just like we did before. Okay. So here you've got this is your opacity. Here's your color meter, and there's little, you can add control points. It's basically just like the other one as far as the volume rendering goes. Okay. I'm going to not focus on the volume rendering here. What I've noticed too is that you can see there's some, what do you call this, like a moire patterns here. There's some kind of ringing. Vapor 3 seems not to do that. It seems like Vapor 3 really does a little bit better job with the, sorry, I'm losing my train of thought. Does a bit better job with the volume rendering. Okay. So we're going to just turn that off for now, but we're going to go to the tab here that says flow. Okay. We'll load instance 1. And then again, we come down here and we have to map the different variables to X, Y, and Z. Okay, so next to steady field here. So let's look at vortex lines. So I'll do WX, WY, and WZ. Okay. I'll put this on the high fidelity. Okay. And then we're going to gradually make this look a lot more interesting. Okay. So the first thing I'm going to do, I'm going to come down here and I want to click Show Flow Seating Settings. All right. And I want more flow lines. We're going to start with 200. Okay. And then I think we need to set these to WX, WY, WZ. I'm not sure. I'll do that to be safe. I think that's only if you use the bias on the distribution there. Okay, so this still looks pretty bad, really. If you the flow lines they're not even rendered very well. They're kind of all over the place. So let's see what we can do. So the first thing we want to do is make these look a bit smoother. So we'll change the line smoothness. So 100, that's pretty good. I'll go back up here. I'm going to turn the accuracy up just a little bit. Maybe I'll do 0.7. Okay, and I think I'll make these even just a little bit smoother. Let's try 150. Okay, we'll leave it like that for a minute. All right, so the next thing we're going to do is we're going to come down here. If we want to, we don't have to have tubes. We could have little points. Okay, we could have arrows, which is hard to see here. If I zoomed in, you'd see there's tons of little arrows. You see these little arrows there. But we're going to stay with tube. And we're going to give it a diameter so we can make these thicker or thinner. So I'm going to make these a little bit thicker. So I'll give it a diameter of 2. All right. Okay, and that's getting better. The next thing I want to do is I'm going to come down here and I'm going to say, all right, how do I want to color these? So instead of saying, let's color them based on a constant value, or let's just give them constant color, let's color them based on something else, like maybe the magnitude of the vorticity vector itself. Okay. So now things are colored by the magnitude of the vorticity vector. Red stuff is basically low entropy, right? And then green and yellow are high entropy. Okay. But what's kind of interesting here is if I want to, I can play with these colors just like before. So I'll stretch that out a little. Can I hit the histogram? There we go. Now I can see my histogram. So if I hit the histo button, and then we'll also make it logarithmic. So now I can see kind of what these different colors correspond to. And what I'll do, I'm going to edit that control point and I'll make this a really dark shade of red. Okay. And I'll drag in the yellow a little bit here. I just heard my wife tell my 4-year-old not to break her brain. Anyway, so now I can play with the opacity here too on these streamlines if I want to. Okay, so I can make the really weak vorticity kind of transparent. And then we just favor certain vortex lines. And then this still looks, I'm going to turn the smoothness up more. It still looks very angled to me. 250, 350. There we go. It's starting to look a little bit better. Okay. But anyway, you get the idea. I think let me just look really quick. I believe I had a transfer function here. So you can save your transfer function. So this is one I created. So you can kind of see there's some little columnar vortices in there around the inner boundary. Anyway, that's all. And then just like in Vapor 2, if you want to animate, there's a little tab here. You can click these arrows to find. There's an animation tab and it works pretty much like in the other one. Okay. So the question, can I briefly cover the capture function? Yeah, sure. So let's turn the flow lines off. You can actually animate the streamlines too. It's kind of cool. All right, so we'll go back over to the DVR tab, which is over here somewhere. There we go. Okay. There's my electricity. You know, I had a decent transfer function for that too. There. Okay. So if we want to, we can go over here to animate. So I'll go ahead and we'll make this go fast. So I'll just click play. All right. And so the way the capture works, so I'll put this back on time step 0. The way the capture works is, I think anytime there's any event, it will capture an image of that. So what I'll do is I'll say begin image capture sequence. And it tells me something about sighting vapor. Okay, and what I need to do is just give it a file name, and what it will do is it will append like 0, 1, 2, 3 for each time step to that file name. So I'm basically giving it a prefix. So we'll just say nm test. I'll hit save. Then I'm going to come over here and I'm going to hit play. And then I'm going to go back to capture, and I'm going to end the image capture sequence. Okay. And then, if I look in that directory, I have one image for each time step from that sequence when I just animated it. Okay. And so I can look at one of these. And there it is. Okay, so then I could put these into my favorite movie maker and get a movie. All right. Okay, that's all I have. Hopefully that's helpful for everyone from getting data from Rayleigh into a 3D viz format. One thing I'll mention is that these cube files, I know those can be useful for other reasons. I haven't pushed it to the repository yet, but I'll add a cube class into Rayleigh Diagnostics so you can just read in the cube file and plot that or manipulate that data if you want to. Okay. That's all I have. Thank you, everyone. Hopefully maybe we can chat next month.